Welcome back to the second part of the tutorial about applied metrology for novel human-computer interaction. In the first part, we started to understand that some novel interfaces of interest for us revolve around extended reality and brain-computer interfaces. And we also saw the first ideas of how applied metrology can help in designing these kind of interfaces and in also interpreting the results. In this other part, we will restart from the question of the last part, where we asked what was happening to the unexpected harmonics content of the brain-computer interface. So we left to the analysis of this kind of system that was a wearable, steady-state, visual evoked potential-based brain-computer interface with the smart glasses for giving stimuli, sensory stimuli that are visual ones, flickering lights, and also with the other component of the shelf that we see here on the right, which is an electroencephalograph with a single channel. And these were also connected because the samples go back to the microcontroller of the smart glasses to be processed. And the idea, at least in the first shots of the usage of this system, was to have a processing based on the amplitude spectra of the brain signals that we acquired from the occipital brain area. But we left on these unexpected harmonics because the idea was that if we are stimulating with a light that follows a square wave, we would have expected only some odd harmonics with a certain scaling law. But we also obtain even harmonics with a different scaling law of the amplitudes. And the literature was saying so far that this is due to the nonlinear effects of the brain. We were wondering in our studies as metrologists if this was also due to some nonlinear and other kinds of effects of the instrumentation. So the first thing that we did, we started analyzing the behavior of the low-cost electroencephalograph. And we started by a procedure that serves to calibrate it. So the idea that we developed is that we have a generator, a voltage generator that generates volts in the order of 1 volt or 2 volts. And this kind of generator, after an amplifier that serves as a buffer, is connected to a calibrated voltmeter. So the multimeter is our instrument to guarantee that we have traceability to the international systems of units. On the other hand, we have to apply this kind of voltage to the input of the device under test, that was the EEG device under test. And to do that, we had to scale from the volts range to the microvolts range, to have the same range of input of the EEG signals that are typically in the order of tens or hundreds of microvolts. So we did that again with calibrated components, and in particular with a calibrated inductive divider and a calibrated resistive divider. The resistive divider had a fixed ratio for the division, while the inductive device allowed us also to modulate the numbers of the division and the partition in order to have also flexibility on this kind of amplitudes to apply to the device under test. We also adopted a norm from the IEEE to characterize the digitizers, and this is basically relying on a sign fitting. And by doing that, we were able to understand if, with respect to the calibrated volt values, we had some errors or some uncertainties in terms of amplitudes, of offsets, possibly also of frequencies. So what we did was to study, first of all, the linearity of this device that was another device from the Olimex. And to do that, we fixed the test frequency to a certain one. Actually, we explored more, but the results here are for 20 Hz. And we varied, thanks to the variable partition factor, the input test voltage in some range that would be of interest. We quantified with the sign fit and then with other analysis of this data how was the relation between the reference input voltage and the actually measured output, and we obtained a graph like this. So you see here in this graph that by measuring multiple points, and each point has a small uncertainty with the small error bar that you could see, which is relatively small, but if you zoom, you could see for each point. We understood from this kind of results that interpolating this kind of point, we had a linear behavior. So first result, this device, although low cost, was not introducing nonlinearities. The second result that we can already see from here is that with respect to the ideal line that will have unitary gain and zero offset, this has again an offset error. So these are linear errors that can be taken into account, but the fact that there was no linearities was already excluding the generation of, at least a significant generation, of the unexpected harmonics. We went on thus to characterize the gain. This time the setting changed because we explored different frequencies, but just one test voltage. And we also did a Monte Carlo analysis with the circuit, which is open hardware, and so we have all the components and tolerances of these components from which we can obtain the behavior with some shades around the nominal behavior. And the plot to which we arrived is this one. Again, the shades are representing around the thick line in the middle, the thick green, a gray line, which will be the expected behaviors with different degrees of probabilities, while the points that are black points that are interpolated by that line is the measured response of the device. So the measured frequency response in terms of gain error. And we discovered that there is a gain error, which would be also negligible in the operation of the PCI as we saw so far. But if we want to correct for this gain error, or if we can act on hardware, if we want to compensate for this gain error, we can calibrate the EEG device to be not only functional and not introduce nonlinearities, but also traceable to the international systems of units. So the result, to recap here, was that the EEG device was not introducing nonlinearities. It had some errors in terms of gain and also in terms of offset that could be corrected or compensated. But so far, it was useful in the kind of experiments that we were doing. We could go back now to the smart glasses. The smart glasses are those that are providing the stimulation. And in this sense, we see here an example of the stimulation of the 10 Hz figuring icon. In this kind of example, what we see is that if we have a 10 Hz stimulation, we have this kind of square wave. We measured this square wave with a phototransducer, which was applied near the lenses of the smart glasses to record the flickering. And if we calculate the amplitude spectrum on this kind of square wave, we understand that, of course, this is not an ideal square wave, because we have already some even harmonics that, although low, are present and relatively significant. But if we switch also to another frequency of interest, which is the 12 Hz flickering icon, in this situation, we could even see that the square wave is not squared anymore, because the duty cycle cannot be 50%. And we understood that this was the case because the refresh rate is fixed. And with this fixed refresh rate, we could not obtain a 50% duty cycle. This means that the light was not following a square wave. It was squared in the sense that it went up and down, but it was not exactly a square wave. And you see here from the amplitude spectrum that, again, this contains some even harmonics, and the spectrum is completely different from what we would have expected in reality. This triggered us also to do further measurements on other kind of smart glasses. You see here that the first column recalls the same that we saw in the previous slide, with the only difference that the amplitude spectrum is now shown with the evaluating scale of the y-axis. In the middle, there is another device from the same company, but different family. And you see here that this square wave is becoming more a triangular wave, and the spectrum changes again. But then we have another device again from Microsoft, which of course is not thought for stimulating users with flickers and adopts a completely different technology that makes the spectrum so different. So in general, the result and big result here was that these are not square waves. And we cannot, in general, say that all the nonlinearities that we were seeing in the unexpected harmonics were due to only the brain. Because now, if we consider the behavior of the stimulation through the smart glasses, and if we consider also the errors and uncertainties in the EEG device, we can go by difference by these two amplitude spectra, and we can now really tell how the brain works. A comment on this is that this could be thought to be caused by the off-the-shelf components that we use. But actually, in also clinical practice, they often use LEDs to stimulate the user with flickering lights. And this means that since LEDs have nonlinearities, if you use them at not small signals when stimulating and when driving them, you have to take attention also to the nonlinearity of the simulation in that case before telling something about how the neuron works and make models of the brain and of the neurons. Another result that is somehow related to this one, but in general relates to the usage of brain-computer interfaces, was that at a certain point we started to characterize the latency that we have in the acquisition, actually the acquisition delays that we have when we use the wearable EEG headset that can be and usually are wireless. So we analyze the different devices with respect to the previous one, but the idea is that if you want wearable and portable instrumentation, you have to take care also of the latency and the delays in the acquisition due to the latency of the communication. So the setup that we created is a simple one to be also easily deprecated. We have a reference generator. This time it's not important if it is calibrated or not in terms of amplitude. The important thing is that it has stability in time. And this provides some square waves. The idea to use square waves was because they have some sharp edges. And we were driving from the same PC the signal generator while acquiring the signals from the EEG device. Again, you can see that before applying the square wave to the helmet, we have to use a divider. Otherwise, we do not reach the range and we do not go down to the range of the microvolts that is needed in input to the EEG device under test. And what we do simply is to compare the reference signal, square wave signal, and the measured one. And here you can see an example or a rough result in which there is already an hint on the fact that there is a delay, which is not negligible, because if you compare the first edge, which is the activation edge of the generator when it starts to generate the square wave, and if you then see the first edge of the signal that is measured, you can see that there is also, qualitatively speaking, a delay between the two. Making it more quantitatively and analyzing 3 different devices with also different sample frequencies of the devices, also different ways of working, because sometimes they have some APIs for the PC, sometimes they don't. You can see here from these results that the distribution of the delays, of these acquisition delays that we measured multiple times, is quite different depending on the device, and it could be also in median value, in this case, quite significant. So these slides recaps also numerically the results and the measurement results that we had, but what is interesting to consider is that when you are measuring some event-related potentials with this kind of interfaces, and if you use this kind of event-related potentials to make also diagnosis of some kind of disease, you have to pay great attention to the device that you're using, because you see in this example an evoked potential measured from the same user with 2 different devices. And the idea is that if you stimulate with a flash at a certain point the user, 300 milliseconds later, you see a potential called P300. It is a positive deflection after 300 milliseconds. And of course, users, because of their subject users, have different responses. They could answer a little before these 300 milliseconds, a little later. If they the evoked response in the answer is too late, this could be pathological. But in our case, if you see the results and if you take also into account the acquisition delays that we measured, we discovered that after the correction, the result for the 2 devices are compatible. While at first sight, it could be seen that in the device 2 there is a greater delay. So if for this user the diagnosis was done only with device 2 and no correction was applied, the clinician could draw a wrong conclusion saying that there is a pathological situation, while there was not. And so this further examples highlights once again the importance to characterize the instrumentation, in this case to measure the acquisition delays, before saying that the instrumentation is not introducing errors and uncertainties, because as applied metrologists, we know that they are always introducing errors and uncertainties. The question is how much and if it is significant or not. So, in conclusion, we saw that human-computer interactions, which was the subject of these two parts of the same tutorial, are evolving, and they evolved from huge electromechanical systems that were the size of our room to things that we can have in our hands, and now today to things that we can wear on our hands. And brain-computer interfaces, together also with extended reality, and some kind of most advanced cyber-physical human-computer interaction. The applied methodology has a crucial role in research and development because it allows not only to design the systems and to be sure that the metrological chain works and is set properly, but also to characterize these kind of systems by taking care of all the errors and uncertainties that they introduce. And by doing so, we can also highlight the bottlenecks to performance. And in this sense, we can also improve or enhance our systems by also tackling those bottlenecks or by explaining unexplained behaviors and understanding more of how the systems that we built and develop work. With this, I thank you again for the attention, and I thank all the partners that through the years have been working with me on this kind of activities. Goodbye.